All right, the semester one final, again, we have two different parts to it. We have the performance final, or the graphing portion of the final, and we also have the multiple choice. We will, like I said a few minutes back, we will absolutely be focusing on both of those. We will absolutely be touching upon both of these. So right now, I actually just realized that I pulled up the wrong thing. This is what we hopefully get into here in a few minutes, but bear with me here just for a second. This is what I wanted to pull up here first. So where we're actually going to begin is with the partial fraction decomposition. Again, par for the course. Hopefully you agree in here that, that looks weird. Let's try this. Everybody cross your fingers. Okay, there it is. That's what we were looking for. All right, so par for the course in here. Again, it's been happening since August. That back in chapter 1, that we have a tendency to make things sound more complicated than what they really are. I would say that partial fraction decomposition absolutely falls in that category. Maybe it would actually find its way to the top of the list. You start saying that partial fraction decomposition, that's, oh man, this seems like it's going to be tricky. I assure you that by the time it's all said and done, of the 6 questions that you're going to have on the graphing portion of your final, this is probably one that, I don't know, maybe the least of your concerns, okay? It really isn't that bad. I promise you that. Sounds much worse than what it really is, okay? But if we were to take a look at the words themselves, when we see partial, what does that mean? Like, not the whole thing? Like part of? Okay? We know what fractions are. Fractions are kind of partials in and of themselves. What about decomposition? Long word. What does that mean? To break down. Good. So, partial fraction decomposition. That means that we're going to be taking fractions and breaking them into smaller parts. It's really all that we're doing. Okay? So, I don't know if you heard, again, Jason was asking about partial fraction composition. Said, well, yeah, you already know how to do that. That's adding fractions. When you were in elementary school, you learned how to add fractions together because you had to find a common denominator. It may have seemed like a hassle, but again, looking back on it now, we know how to find a common denominator. Then we can actually combine or compose these fractions. All that we're doing is we're splitting it apart. Okay. So if we were to look at this, and please don't write this part down, but if you had something like 5/8, is this the same as 4/8 plus 1/8? We know that, right? Nobody's surprised to see this. So what may look a little bit more intimidating is if we wrote that as 1/2 plus 1/8. Would we agree that that would be a partial fraction decomposition? That's really what we're doing, but with much more complicated looking stuff. Okay. Now the ways that we're going to go about obtaining these decompositions may look a little bit different, but I assure you it's not going to be too tricky, not too demanding. Okay, so if we're going to go ahead and jump directly into this first problem, we have x plus 7 over x squared minus x minus 6. Where do we begin? Anytime we have one of these rationals, where should we start? Factor the denominator. Why factor? You're right, by the way, but why? What is our goal? What are we hoping happens? Yeah, we're hoping that we have some common factors that divide out, and this whole thing simplifies down. Still where we want to start, still where we want to begin. So, is everybody okay with me saying that we have x plus 7 over, when I factor, we're going to call that x minus 3 times x plus 2. Calibration's off a little bit. Okay, is everybody good with that? X minus 3 times x plus 2, that's what our denominator would have factored to. Are there any cancellations that are going to occur? Any common factors, numerator, denominator? No, but it was worth a shot. Okay, not only was it worth a shot, but we have to do that anyway with partial fraction decomposition. Okay, so what we're going to say is that if this is how our denominator breaks apart, think about what we just did with that 5/8 thing. We are also saying that we're going to have something over x minus 3 and some plus something over x plus 2. Okay? That's where this is going to begin. We factor the denominator, and those factors will be my denominators of the sum. And what about the numerators? I guess that's kind of what we're trying to figure out. Okay? That's what we're going for. So frankly, we need placeholders. Since I'm really boring, I usually just use A and B. But in all seriousness, it's just a placeholder. You can put anything you want up there. You could you draw a star and a dinosaur for all I care. It doesn't matter. You just need to hold the place. I have a weird feeling I know who's going to draw a star and a dinosaur now when the time comes. But again, it could be anything. You could use, personally, I would encourage you not to use X because we already have the variable X in this one. But I mean, you're just holding the place. I know that I've had students that have used X and Y before, and they say, no, that's a capital X. My variable's a lowercase x. I'm like, yeah, you're playing with fire right now, but if you can keep it straight, go ahead. But it really doesn't matter. That's not going to factor into our overall answer, so to speak. Okay? So is everybody good with how we would break this apart so far? Obviously far from an answer, but this is where we begin. Okay, now from here, how many people just love working with fractions? Show of hands, anyone? Anybody say, yeah, anytime I have all these integers, like that's all messed up. I want to turn them all into fractions. Anybody want to do that? I didn't think so. Okay, so if we have the choice, and I'm going to put myself at the top of that list as well. Why would we intentionally choose to work with fractions if integers are an option? Okay, so when we are looking at what we have currently, would it be nice if we maybe could get rid of the fractions? If we could rewrite this in a way such that we did not have fractions, that might be something that's worth looking into. Would you agree with that? Yes? No? Okay. So give me a second here. I'm just going to copy this down. A little bit more space. Okay. So let's focus on the left side. What would if that's the goal, I don't want fractions anymore. I want to get rid of fractions. What do I have to do? What would I multiply the left side by in order to not have a fraction on the left side any longer? Did I hear the denominator? Yeah, so if we multiplied times x minus 3, x plus 2 over 1, would that do it? Would that essentially cancel the fraction on the left side? But there's a catch, isn't there? Yeah, if we do this on the left side, we have to do this on the right side. Specifically, we have to do this to everything on the right side. And that's exactly what we're going to do. Multiplying both of these terms times the denominator over there. All in an attempt, once again, to not have fractions. I know that the x minus 3's are going to cancel. I know that the x plus 2's are going to cancel. So my left side just becomes x plus 7. Looks a whole lot simpler, doesn't it? Okay? Now the part that we're maybe a little nervous about is we had to do the same thing on the right side. But again, we notice that these x minus 3's cancel. So what we're left with is a times quantity x plus 2. Over here we had the x plus 2's that canceled. And we're left with plus b times quantity x minus 3. Now this, again, is not my answer. This is what we are going to refer to as our model. So just like we had back in chapter 9 with the binomial expansion, we created a model so then we can work with the model. And that's exactly what we're doing here. Okay? Now, something tells me that after we do one or two of these problems, you're going to see shortcuts and abbreviations of how you could get to the model. It's really not super complicated. We'll discuss as we go. But this is the model nonetheless. Our job is to solve for A and to solve for B. We're not trying to solve for X. We're trying to solve for A and B. Remember what we had back here. This is what we're trying to create. What is that numerator? What is that numerator? Okay? But we have a little bit of a problem here. How many variables do we have? Currently I have 3 variables, which is like too many, right? Now, if you're wondering why in the world, because so far, again, this was section 7.4, right in the middle of our chapter that was dealing with systems of equations. Could we solve this using systems? Yes, we could. It's not going to be, in my opinion, one guy's opinion here, that's not going to be our best option. There's a much faster, more efficient way. All right, let's go ahead and think of it this way. We want to find A. Nothing's really saying that we have to start there, but if we wanted to find A, All right, what would happen? Now, we do have the ability, since we're not trying to solve for x, we have the ability of just saying, all right, let's let x equal 10. If I let x equal 10, could we then solve for a? Still have two variables. We don't know b. Okay? What if I let x equal, what if x equals 0? Would that do it? Still no. It's not going to work out. So what we have to do is that if we let x be some specific value, we have to somehow be smart about this and do like the whole 2-for-1 type thing. We have three variables. We need to let x equal something to where we get down to one variable. So what if we were to let x equal 3? Would that do it? Remember that I'm trying to solve for a. Now, of all things, I don't care about this one, I don't care about this one, it's this guy right there. If I let x equal 3, what's going to happen in the parentheses over there? 3 minus 3 is 0, and then when I multiply 0 times b, what happens? It's gone. We're down to one variable we can solve, okay? So here's the catch. When we find a, what we want you to think is what we're really doing, we're trying to cancel b. Okay? That's really what we're trying to do. What's the value of x that's going to cancel b? And then from there, it's literally, again, just plug into your model. We said that to cancel b, we're going to let x equal 3. So that means that we're going to rewrite this. Everywhere that I see an x, I'm going to put a 3. So we really have 3 plus 7 is equal to a times 3 plus 2 plus b times 3 minus 3. We evaluate this on the left side. 3 plus 7 is 10 equals a times 3 plus 2 is 5 plus b times 3 minus 3 is 0. And here was the beauty. B times 0 cancels. It's gone. Leaving us 10 is equal to 5a. When I divide both sides by 5, we can finalize this and say that a is how much? A is 2. All right, now that was fun, right? I know it doesn't look like systems of equations, but guys, that's systems of equations. Again, we use substitution to cancel. We didn't set up the system. I feel like we could. That's why it lives in chapter 7. Why make it harder than it has to be? All right, so that was so much fun solving for A. Let's go ahead and do the same thing solving for B. Now, that's what we're going to write up, because that's our goal, which it is the goal. I don't want to send a mixed signal here. We are trying to find B. What are we really going to do, though? We're really going to cancel A. That's really what's happening. So if we wanted to cancel A, what are we going to let x equal? Yeah, we're trying to create a 0 with that a. So again, x is going to be then equivalent to -2. Now when we plug in, everywhere we see an x, we put a -2. So back to the model, -2 plus 7 is equal to a times. Now we have -2 plus 2 plus b times -2 minus 3. And we clean this up. -2 plus 7 is 5. A times -2 plus 2 is 0. B times -2 minus 3 is -5. A times 0 cancels. 5 is equal to -5b, at which point we know the b is. All right, so very important. We found A, we found B. Or you found star, you found dinosaur. Whatever it is that you chose to use for your numerators. Okay? We have that A is 2, B is -1. We have to understand that saying that A is 2 and B is -1 doesn't really solve anything, because not everyone, chances are not everyone used the same numerators. Again, A's and B's or whatever. Okay? So we can't just say, oh yeah, A equals 2 and think that we're done. Okay? Also, the order matters. What if I would have factored this and said that instead of saying x minus 3 times x plus 2, what if I would have said x plus 2 times x minus 3? Then A would have been over x plus 2, B would have been over x minus 3. That would change things. Literally, if we did it that way, we would have gotten that A was -1 and B was +2. So the way that we have to finalize our answer is that we have to plug these back in. So if A was 2, B was -1, we come back here and we're going to rewrite where I had an A. Remember that was 2 over the x minus 3 plus we said B was -1 over the x plus 2. And this is what we refer to as a partial fraction decomposition. We have the original equals, and we break it down that way.